Okay, so good morning. Now we are going to discuss about the last type of counters, which are synchronous counters. So in the previous class we were discussing about different types of asynchronous counters. Now we will see what is a synchronous counter. But before going to that, I'll just give you a particular problem which is associated with asynchronous counters. Let us assume that we are in this particular situation, and this is a scenario that I am considering. It can happen in any case of regarding this asynchronous counters at any state. Okay. So assume that initially I am in state 0000. So assume that I am having an up counter. So after 000, automatically it has to switch to 7. Sorry, if I am having a down counter, then after 0, again I have to start from 7, right? So I have to start from 7. So here what we are assuming is that whenever I am giving a clock, at that moment the output will change the state. But that is not actually true. Why? Because there will be some delay in the speed clock. So output will not change at that particular instant. After a bit amount of time or after a small gap, then only the output will get changed, flipped. Okay, so in that case, I can redraw the speaker like this, because whenever this clock is going from 0 to 1, this particular, let it be this be Q0, this be Q1, and this is Q2, and this flip flop will go high. But actually, after it is going from 0 to 1, after some time only it will change, because there is some delay between the input and the output. So that delay I am showing here. Okay, that delay I am showing here. And similarly, here also, for the 0 to 1 transition, this output will be high. So here also, here we are having 0 to 1. So after that, we can have some delay, and after that delay only this output will become high, right? So this is the actual case. This is actually it will happen, but in all the cases we'll assume that suddenly there is no delay between input and output, and we'll assume that everything will happen as we what we have planned before. So this is the case, and here also, since we are getting the input at this time, then after some time only it will get activated. So there, here is also some delay. So actually there is a total of this much delay is there between the current clock and the final output. Okay, so in between you can say that actually what we are doing here is the 0 0, here we are assuming that this is 1 1 1. So we are expecting 7 here. But in between this 0 and 7, there are some state transitions are happening in between. How? See here, this is 0 only, and here this is 0, and here this is 0. That's fine. But take the next one. Here it becomes 1. Okay. Here it becomes, this is 0, and here also this is 0. So what is 0 0 1? Or if you are taking it as yes, this is Q0. So what is 0 0 1? 0 0 1 is 1. So if it was 0 0 0, then it is for a small duration it is going to 0 0 1. And what happens in the next moment? This is 1 only. Then here also it is, here it becomes 1. And what is here? Here again it is 0. So 0 1 1. So 0 1 1 it is going for a small duration of time. And after that, after this much time, then only it is going high all. So now 1 1 1. 1 1 1 we have. So actually what we are expecting is from 0 0 0, suddenly it will go to 1 1 1. That is what our expectation is. But actually how it is happening, in between, for a small duration of time, for a very small duration of time, some state changes are happening, but that is not visible to us. So but in between it is happening. So this is 0 0 1, and the 0 1 1 it is happening, and after that only it is coming to 1 1 1. But for the maximum duration it will be at state 1. But for this much duration it will be at 0, and this will be at 3. 0 1 3. Then after that only 7 is coming. So this particular problem is known as a glitch. Okay, why this is happening? Why this is happening? Because in case of asynchronous counters, we are giving clock, our clock is given from the previous state. Okay, so when we are getting, after getting the previous state output, then only we can feed that input to the clock of the next flip-flop. So there will be, that delay will be there when passing the input to the next state. So the problem associated with this asynchronous counters is known as a glitch. Just because of the time gap or a small time duration that is happening in between the, because of the delay between the flip-flops. So that is why it is known as a glitch. So in order to avoid this particular problem, what we are doing is we are giving clock to all the flip-flops at the same time. So everything will happen at the same time. So all the transitions will happen at the same time. So in that way we are managing, or we are trying to avoid this glitch issue, the glitch property in this asynchronous counters. Okay. So now I think we can look into the synchronous counters. So what is a synchronous counter? In case of the synchronous counter, we can say that all the flip-flops are connected, and the same clock is applied to all the flip-flops. We are applying same clock to all the flip-flops. So we can assume that all the flip-flops will change its state at the same time. Glitches will not happen at all. So that is what assumption is. Okay, so this is a synchronous counter. So clock is given to all the flip-flops at the same time. That is why it is known as synchronous counters. Now we are going to discuss what are the steps to be followed for designing a synchronous counter. Okay. Okay. So now we are going to discuss about what are the various steps to be followed when designing a synchronous counter. And first of all, we have to see what type of flip-flop that you are, what type of counter that you are going to design. If it is a 2-bit up counter, you have to use 2 flip-flops. So first step in doing designing the synchronous counter is identifying the number and the type of flip-flops. Number and type of flip-flops. So we know that we are having different types of flip-flops. JK flip-flop is there, T flip-flop is there, D flip-flop is there. So using any of these flip-flop, we can design these counters. That is not an issue. Okay, we'll see the different designs using different types of flip-flops in the coming lectures. And first thing that you have to do is identify the number and type of the flip-flop that you are going to use. Then second step is, if you are using a JK flip-flop, then you have to find out the, you have to know the excitation table flow for that particular flip-flop. If you are using T, then you have to know the excitation table for that flip-flop. Then that is the second step. As a third step, what you have to do is find the state diagram and the circuit excitation table that we'll see in the coming now, that we are going to see now. So we have to draw the state diagram and the circuit excitation table. Then after that, for finding the equation, Boolean expression for each of the input, you have to use K-map. So you can use K-map to find the input expression of each flip-flop. And finally, after finding the expression, you can draw the logic diagram of the counter. Okay, so these are the steps to be followed. And now we are going to decide a 2-bit synchronous counter. 2-bit synchronous counter, very simple counter, 2-bit synchronous counter that we are going to decide. Okay, so what is our first step? What is our first step in decide? What is our first step? The first step is we have to find the number and type of flip-flops that we are using. So for deciding a 2-bit counter, how many flip-flops we need? For deciding a 2-bit counter, we need 2 flip-flops. So the first step is we need a we need 2 flip-flops. Then what is the type of the flip-flop that we are using? You can use either JK or T or D flip-flop. Whatever we are choosing, you have to design based on the excitation table of the corresponding flip-flop. Now here I am using a JK flip-flop. I am using JK flip-flop for designing this particular counter. You can use T or D. Okay. Now here I am using JK flip-flop. Then second step is I have to find the excitation table of that particular flip-flop. For JK flip-flop, how to find the excitation table? We know that we are having states Q, let it be Qn, and let the next state be Qn plus 1. This is the present state, and this is the next state. Okay, so if this is the present state and next state, how the J and K input will be for this particular case? How J and K input will be? Okay, so if we are having current state as 0 and next state and changing, next state is also 0. We are having four different combinations. If it is 0, current state is 0 and next state is also 0. So for what all input combinations you will get this particular state. For what all input combinations you will get. So if j is equal to 0, k equal to 1, and if j is equal to 0 and k equal to 0. In these two cases you will get 0 as the, if the present state is 0, next state will also be 0. So this is the first condition. Okay, then second is if our present input is 1 and the next input, present input is 0 and next input is 1. This is the present state and this is the next state. So for which all values you will get this particular condition. Present state is 0 and next state is 1. If the j input is 1 and k input is 0, you will get this state. And one more case is if j input is 1 and k input is 1, then also you will enter into this particular state. This is the second case. Okay, in the third one, if the current state is 1 and the next state is 0, current state is 1 and next state is 0, next state is 0. So then we are having 0, 1 or 1, 1. In these two cases, you will get 1 and 1 as the present state and 0 as the next state. And the last case is current state is 1 and the next state is also 1. In what all case you will get this state, this particular condition, you will enter into this particular condition, that is 0, 0 or 0, 1, 0. So these are the various cases. So these are the various cases in which you are getting this type of transition. Okay. So from this you can see that here j is 0 in both cases. Only k is changing. So here this we can replace with 0x. This can be taken as a dot here. This can be taken as a dot here. So here 1 is common, j is 1 and k is changing, right? K is 0, 1. So we can take it as 1x. Here x is nothing but it can be 0 or 1. Can be taken as a dot here. Here see j is changing, k is 1. So how we can take this as x1, x1. And what about this? Here j is changing, k is 0. So this can be taken as x0. So this is the excitation table for this JK flip-flop. Excitation table for JK flip-flop. So I will draw right here. If Qn and Qn plus okay, so we are in the second step. We have to find out the excitation table of this flip-flop. Since we are using JK flip-flop, the excitation table is this. So this is a present state and next state, and here this is the excitation table, and I have drawn a summary of this table. 0 0 means this is 0x, this is a downget, so it means that it can be either 0 or 1. 0 1 means 1x, and 1 0 is x1 and 1 1 is x0. Okay, so this is a summary of that, and now we have to draw the state diagram and the circuit excitation table, and we'll see what it is. Okay. So this is our second step, and now we are moving to the third step of the design, and in this third step we have to draw the state diagram. State diagram means here I am using a 3-bit synchronous going to design a 3-bit synchronous a 2-bit synchronous counter. Okay, I didn't mention whether it is up counter or down counter. So let us assume that I am going to design an up counter. So what will be the if it is 2-bit, so we will be having two flip-flops. So how many states are possible in that? How many various combinations are possible? So if it is 2-bit, you can have only 4 states. That is 2 power 2, which is equal to 4 states are possible. So what are the various states? This bits can be, that is, we can have Q1 and Q0. It can be 0 0. Then can be 0 1. Then you can have 1 0. And you can have 1 1. So after 1 1, if it is an up counter, it has to go to 0 again, right? This is the transition diagram, state transition diagram. Okay, so this is state 0, this is state 1, this is state 2, and this is state 3. You can see. So this is the state diagram. So from now we know after 0 0, what will be the next state? Next state is 0 1. After 0 1, next state is 1 0. After 1 0, next state is 1 1. After 1 1, next state is 0 0. This is how this particular order is. Okay, so this is the state diagram. Now we are going to draw the circuit excitation table. Okay, so we'll see how we can draw it. We know that we are having two inputs, Q0 and Q1. We are having two input, Q0 and Q1. So this is our present state. This is the present state. Then in the next state, assume that you are having Q0 star and Q1 star. Okay, this is my next state. So I am having, it means that I am having two flip-flops, right? I am having two flip-flops. Output of this is Q0, and I am having another flip-flop. Output of this is Q1. And for this flip-flop I am having J0, K0, and for this flip-flop I am having J1, K1. So I have assumed that I am using JK flip-flop. Okay, so what we are going to find out is I want to get the expression for this inputs. What input I have to give to make this as a up counter. Okay. Now, see, this is Q0, Q1, and for this Q0, I am having four inputs. One is J0, then K0 is there, then J1, K1 is there. So these are my inputs. Okay. So I want to find expression for J0, K0, J1 and K1. That is what we are going to finding out. Now, and assume that my current state is 0 0. So what will be the next state? If the current state is 0 0, in case of up counter, what will be the next state? What will be the next state? It will be 0 1. Right? So this is the current state, this is the next state. Then if the current state is 0 1, what will be the next state? Next state will be 1 0. If the current state is 1 0, what will be the next state? Next state will be 1 1. If the current state is 1 1, what will be the next state? 0 0, because it has to repeat. The cycle has to repeat. So if it is 0 0 current state, then next I will go to 1. If 1 is current state, next I will go to 2. If 2 is the current state, next I will go to 3. If 3 is the current state, again I will switch back to 0. Okay, so this is the order. So 0, this is 1, this is 1, this is 2. 2, this is 2, and this is 3, and this is 3, this is 0. So 0 to 1, 1 to 2, 2 to 3, 3 to 0. That is our cycle, right? So state transition diagram 0, 1, 2, 3. In this order I have to move. That is what I have shown here. Okay. So I'll remove all these unwanted things. Okay. So this is my present state and next state. Now, based on this excitation table, I have to fill this J0, K0 and J1, K1. See, for that I'll take current state Q0 and the next state Q0 star. Okay. What I'll take current state as Q0 and next state as Q0 star. So if Q0 is the current state and Q0 star is the next state, what is JK? So from where we will get it? If current state is Q0, that is we can take it, this is Qn plus 1. This is the current state Q0, next state Q0. Then what is J and K? J and K is 0x. So if current state is 0, next state is 0, J and K is 0x. Similarly, you take the next one for Q1. Okay. For Q1, current state is 0. What is the next state? 1. So 0, 1. Current state is 0. Next state is 1. If it is 0, 1. If it is 0, 1. What is JK? JK is 1x. So for Q1, J1, K1 is 1x. K1 is 1x. You have to listen carefully because you can expect minimum one question from this part, designing of a synchronous counter. Okay. So this part is very, very important. Now, next. Okay, this is over. Now I take next Q0. Q0 is 0. What is Q0 star? 1. 0, 1. 0, 1 means, 0, 1 means what is JK? 1x. So I will write 1x. J0, K0 is 1x. Then I take Q1. Q1 is 1. Q1 star is 0. 1, 0. What is 1, 0? 1, 0 is x1. So I will put x1 here. Okay. Now, what is next? This is over. Then current state is 1 and next state in Q0 is 1. So 1, 1. 1, 1 means x0. So I will put x0 here. Then take the next input 0 and 1. Q1 is 1 and Q1 star is 1. So current state is Q0, Q1 and the next state is Q1 star. So 0, 1. If it is 0, 1, it is 1x. So I'll put 1x here. Okay. Now I'll move on to the next state. That is Q0 is 1 and Q0 star. Next state is 0. 1, 0. 1, 0 means x1. x1. Then next is Q1. Q1 current state is 1 and next state is 0. 1, 0. 1, 0, it is nothing but x1. Okay, so I hope this is clear for you. And now, with this, I will try to find out. Now, I have got what is J0, what is K0, what is J1 and what is K1. So, from this, using K-map, I will find the expression for J0, K0, J1 and K1. What are the inputs? Inputs are Q0 and Q1. Okay, so I am going to wrap this excitation table. Here, we are having four inputs. This is for J0, this is for K0 and this is for J1 and one more we need to have, this is for K1. Okay. Now I am using K-map because we are having only two inputs Q0 and Q1. So you need to have only 4 columns. And this is Q0 and this is Q1. This is Q0 and this is Q1. This is Q0, Q1. This is Q0, this is Q1. Okay. Now you can see this is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Right? And now you can fill this. This is 0, 1, x, x. 0, 1, x, x. How it will be represented? 0, 1, x, x. Then next is x, x, 0, 1. So two dot pairs x, x, 0, 1. Next is 1x, 1x. 1x, 1x dot pairs. Then last one, k1 is x1, x1. So this is k1 is x1, x1. Okay, now we can minimize this. So how we can minimize? Just try to find out how many groups can be formed from this, and this will form a group. Here this will form a group, and this whole thing will form a group. Here also this will form a group. So what is the expression for this? J naught, then J naught is, it is nothing but Q1. Then what is K naught? K naught is also Q1. Then what about J1? J1 means all we can select together. So J1 is equal to 1 and K1 is also 1. So this is our normal K-map simplification. Okay. So now we got the expression for J0, K0, J1 and K1. Right? So now I am going to wrap this, and okay. So this was our fourth step. The schema simplification was our fourth step. Now we are going to our fifth step. Fifth step is we are going to draw the logic diagram for this particular counter. And since this is a 2-bit counter, we will be having two flip-flops. Two flip-flops we are having. So two flip-flops, and let this be flip-flop 0, and let this be flip-flop 1, and this is Q0, this is J0 and K0, this is J1 and this is K1, and this is Q1. Okay. So what about clock? Since this is a synchronous counter, we are giving clock at the same time. Same clock is given to all the flip-flops. But in the previous asynchronous case, we are taking from output of the previous flip-flop. Here clock is given as a common input to all the flip-flops. Okay. Now this is Q1. Now we can see from here what is J1 and K1. J1 and K1 are both 1. Okay. So what I will give? I will give a logic 1 here. Logic 1 here, and I connect to both J1 and K1. I connect to both J1 and K1. Then what about K0? K0 is equal to Q1, and J0 is also Q1. So Q1 will be connecting to J0 as well as K0. J1 will be connecting to K0 and J0. Okay. So from here you can take Q1. From here you can take Q0. So in this connection, if you are having this particular connection, then we can say that this particular counter will work like a 2-bit up counter. Okay, so this is the whole circuitry of designing a synchronous counter, a 2-bit counter. And similarly, if you are having a 3-bit counter, what we can do? Instead of Q1, Q2, here we have only Q1 and Q0. And if it is a 3-bit counter, you will be having Q2, Q1, Q0. So you have to have 3 flip-flops. So J0, K0 will be there, J1, K1 will be there, J2, K2 will be there. So for that, for each of those inputs, you have to find out the logic expression. Then you have to realize this using the logic diagram. Okay, so that is all about this synchronous up counter. Okay.